Welcome to example number 12. In this example, we're looking at a satellite that is moving in an elliptical orbit around the Earth. Some data has indicated that the closest approach distance, this is called the perigee point, it has a distance from the center of the Earth given as 8.37 times 10 to the power of 6 meters. We also know that when it's furthest away from the Earth, which is called the apogee, that distance, that greatest distance, is given as r sub a is equivalent to 25.1 times 10 to the power of 6 meters, again from the center of the Earth. We also know the satellite has a speed at the perigee point, the closest distance. That velocity p is given as 8,450 meters per second. In this particular example, we're asked to find out what is the speed of the satellite at apogee. So what is v sub a? So as we observe the satellite moving around the Earth in a elliptical orbit, imagine if we take say just this particular point. There's really only one force acting on it, and that's the force of gravity. And this force is acted directly towards the center of the Earth, right along the axis of rotation, which is shown by this dashed line. So if we were to look at the net torque acting on this satellite of mass m, sum of torques, it would be equal to the force of gravity multiplied by the distance r, which is going to be variably changing, times the sine of the angle between the force vector, which is directed towards the center, and the radius vector, which is along the same line. So either the sine of 0 degrees or the sine of 180 degrees. And the sine of 180 degrees, or 0, will be basically 0, so the net torque is 0. And if you recall, we talked about earlier in the notes about angular momentum. If the net torque, which is equal to I alpha, which you can derive to be equal to the change in the angular momentum over the change in time, if this net torque is 0, if the net torque is 0, that means then if the left side is 0, then the right side has to be 0. So that means that the change in the momentum, angular momentum, must be 0, which essentially means that the initial momentum and the final momentum are equal to each other. So to solve this problem, we're going to be using conservation of angular momentum. The angular momentum of the satellite as it moves along through here is constant at all times. So that means that the angular momentum at apogee, we'll write that as L sub a, must be equal to the angular momentum at perigee. We'll write that as L sub p. And as you may recall earlier in the notes, the angular momentum is given as the rotational inertia multiplied by the angular velocity. So then we can substitute this in, and we're going to be using the rotational inertia it has at point A multiplied by the angular velocity at point A, which is equal to the rotational inertia it has at point P, and the rotational velocity or angular velocity at point P, perigee. And since these are just simply point masses, you can assume that the satellite is just singly a point mass at a distance r, or distance r over here. We're now going to replace the rotational inertia for each of the individual positions at apogee and perigee with m times r squared. M will be the mass of the satellite, but r will be changing as it goes from perigee to apogee. So we're going to have mass of the satellite multiplied by r sub a, that's that radial distance from the center of the Earth to apogee, multiplied by the angular velocity at a. That's equal to the mass of the satellite multiplied by r sub p at perigee squared, multiplied by the angular velocity at point P. And interestingly, you'll see that the mass of the satellite cancels out, which means it's irrelevant to solving the problem. And we're not given angular velocity at point P. We're actually given the linear velocity or tangential velocity, so we'll need to get that into there somehow. If you recall, the linear velocity is equal to the radius multiplied by the angular velocity. So we're going to replace that angular velocity with the linear velocity divided by the radius. So let's go ahead and replace that for each one here. R sub a squared multiplied by the velocity at a divided by the radius at a equals the radius at p perigee squared multiplied by the velocity at perigee divided by the radius at perigee quantity squared. And you can now do some cancellations. So you'll note that this radius will cancel out with one of these and on the other side as well. And so beautifully the formula comes out to be r sub a multiplied by velocity a equals r sub p multiplied by velocity p. Sometimes you often see people put the m in here, and that's true. So if the mass were to change of the satellite as it moves, then that would consequently change other things over here, like the radius or the velocity. But since the mass cancels out, and we're assuming that the mass of the satellite remains constant, we can cancel it out. And let's solve for the velocity at apogee, which would be the radius at perigee times velocity at perigee divided by the radius, the radius at apogee. So now making our substitutions and then plugging into our calculator, we're going to get an answer of 2,820 meters per second. So two quick things to notice again is it's independent of the mass because the mass cancels out, so that's not relevant, the mass of the satellite. Secondly, as your distance gets further, as say r gets larger, then the velocity is obviously going to get smaller. It's kind of like if you're a figure skater. If you're a figure skater and you're actually moving your arms inwards, then that's going to cause you to move at a very large angular velocity as your radius decreases. Or if your radius increases, then your angular velocity is then going to decrease. This is all due to conservation of angular momentum. So if the satellite was moving in a perfect circular orbit, then the velocity would be constant. By the way, this doesn't just apply to satellites revolving around the Earth. This can be applied to the orbits of planets revolving around the Sun. More importantly, if you remember Kepler's 3 laws of kinematics that we talked about in Chapter 5, planets revolve around the Sun in elliptical orbits where the Sun is at one of the foci of the ellipse. Second one, which we didn't talk about too much, but this radius vector r sweeps out equal area, so area 1 here and area 2 here at a different time interval, or different time of the year, for example, as the planet's revolving around the Sun. These will be equal areas and equal time intervals. And in fact, this law, the second law, which we didn't talk about it too much, is actually derived from the conservation of angular momentum. And that's it for this example.